Hello there! In this lesson, we're going to look at the titration process as it applies to weak acids and bases. This lesson is going to put together everything we've done that involves weak acids and bases and the equilibrium that is related to them. It has buffers that we just finished in the last lesson, and it also has, of course, weak acids, weak bases, strong bases, all that stuff from the whole unit all comes together right here in one neat little package. Alrighty, so I don't know how much you remember from previous years about the titration process, but it involves using these little skinny tubes called burettes that have this valve at the bottom here called a stopcock that allows some of the solution to be added a drip at a time into this beaker at the bottom. And so what you do is if you have like an unknown concentration of an acid down here, you can add a known concentration of a base from up here, and then when you get to the equivalence point, you get to the point at which the solution is neutralized, then you can tell the concentration of the unknown from the amount of the known that you used. So at that point, the moles of the hydrogen ions from the acid will be equal to the moles of the hydroxide ions from the base, and you'll be able to determine the concentration that was unknown using this little nifty relationship here. So for example, we have a base what we got here. We got 0.22 moles per liter of the acid, and we got 0.35 moles per liter of this base. And so in this case, we want to know the volume of the base that is going to be needed to neutralize all of that acid. So we've got the concentration of the acid, we got the volume of the acid. We have the concentration of the base, and so we're looking for the volume of the base. So you can rearrange that so the volume of the base is equal to the concentration of the acid times the volume of the acid all over the the concentration of the base. So let's stick that in here, and we will be able to work out that the concentration of the acid is 0.22 moles per liter. The volume of the acid is 15 milliliters. And we're going to divide that by the 0.35 moles per liter for the base. Now I could convert this into liters if you want, but since it's just a ratio, we'll just keep the same units. And whatever answer we get here will be in milliliters as well. So I get 9.4 milliliters of the base being added in order to neutralize that acid. So there you go. That's an easy calculation to be able to determine the quantities of unknown from the ones that you have. So now the pH at that point in which the acid and base have been neutralized will depend on what type of acid and base are being neutralized. So when it's a strong acid and a strong base, like HCl and NaOH, you'll end up with a salt that is neither acidic or basic. So you'll end up with like sodium chloride. And so the pH at the equivalence point will be right at 7 because the salt that you end up with is a neutral salt. Now we know that weak acids, when you neutralize them, they produce conjugate bases, which means that at the equivalence point, you're going to have a salt that's slightly basic, right? So when you neutralize a weak acid with a strong base, what you end up with is that weak base, that conjugate base, that's produced at the equivalence point. So your equivalence point won't be right at 7, it'll be a little above. And the opposite happens if you have a base and you're neutralizing it. You'll end up with a salt that's slightly acidic, right? Because it's a conjugate acid that gets produced. And so that pH at the equivalence point isn't always at 7. It'll depend on the salt that's formed. So to determine that pH at the equivalence point, what you have to do is look at the type of salt that's being formed and then find the concentration of that salt, right? Figure out the moles, figure out the volume, and divide. And then get the equilibrium constant for that salt, for the base of the acid. In this case, we're neutralizing a weak acid, and so what we're going to end up with is a conjugate base. So here's an example. Here's nitrous acid, and if you neutralize it with this sodium hydroxide, you're going to end up with this conjugate base that is a proton acceptor. when you have neutralized all of the acid. So what we need is the concentration of that acid and then the Kb. So you need Kb and you need the concentration, and then you can work out the pH. All right, so let's work out the pH at the equivalence point for this example. We are given this 15 milliliters of this 3 molar weak acid, nitrous acid, and we know that the conjugate base that's going to end up being produced is going to be the nitrite ion, right? And so the neat thing is that you're going to have the same number of moles of nitrite as you had of the nitric acid, because at equivalence point, all of this is going to get neutralized. So let's figure out how many moles that is. So I'll say moles equals 0.015 liters, that's the 15 milliliters, times 0.30 moles per liter. And that comes out to 4.5 times 10 to the negative 3 moles. Now we're going to dilute that, because in order to neutralize that, we added 25 milliliters of this base. So the total volume then is going to be 40 milliliters total. Right? So the concentration of NO2 is going to be this many moles, 0.1234, is that right? No, get rid of one of these zeros. 1, 2, 4, 5, yeah. Moles in 0.04 liters. So let's divide that, divided by 0.04 equals. So this is the concentration of our conjugate base. We'll keep extra digits for now. So that's the concentration of NO2 minus. Now, we need the Kb in order to work out the pH of this solution. So Kb is Kw divided by Ka. So that's 1 times 10 to the negative 14 divided by 4.0 times 10 to the negative 4. So let's see what this works out to be. 1e14 negative divided by 4e4 negative equals 2.5 times 10 to the negative 11. That's our Kb. So then the final thing is to work out the pH, and we can use the same relationship that we always did. So remember, Kb is the concentration of hydroxide times the concentration of the acid all over the concentration of the base that we're starting with. So this is going to be x squared all over the concentration of the acid, which is 0.1125, or base, I should say, and equals our Kb, which is 2.5 times 10 to the negative 11. And so we'll multiply those two, so times 0.1125 equals, so x squared equals 2.81 times 10 to the negative 12. And then we'll take the root of that, and we get down to x equals 1.7 times 10 to the negative 6. And so that's moles per liter, and that's our concentration of hydroxide. And then so our pOH then is the negative log of that. pOH is 5.77, 5.8. And that means our pH is 8.2. There you go. The next point of interest in our titration journey here is the relationship between the process of titration and equilibrium constant. So if you remember our good old Henderson-Hasselbalch equation here, the pH is equal to the pKa plus the log of the concentration of conjugate base over acid when we're talking about a weak acid being neutralized. So there's a neat thing that happens halfway to the equivalence point. So we've been engaged with the equivalence point for the past few minutes. And at halfway, that means the concentration of the base will be the same as the concentration of the acid. So you would have turned half of this into this, and so they'll have equal quantities, equal number of moles in the same volume. And what happens is that the log of those two values ends up being 0, and halfway to the equivalence point, the pH will equal the pKa, and that's an easy way to work out the equilibrium constant from a titration. Alrighty, so from a titration, once you've plotted it all out, you might see that the pH halfway to the equivalence point was 4.2 and want to find out what the equilibrium constant is for that acid. So at that point, pH will equal the pKa, and so that means 4.2 equals the pKa. And so if you want the Ka from the pKa, it's the same as getting the hydrogen concentration from the pH. And so what you do is you just take 10 to the negative 4.2 will equal the Ka. So 10 to the negative 4.2 works out to be 6.3 times 10 to the negative 5, and that's our Ka. So that's a handy little trick that you can use to interchangeably work out the halfway equivalence point and the equilibrium constant. Our next point of interest on our titration curve is the phase in which you have similar quantities of weak acid and conjugate base, or weak base and conjugate acid, which is by definition a buffer. And so the pH in this range can be worked out the same way that we worked out the pH of any other buffer. This buffer is just made, instead of by adding conjugate base or acid from a salt that is externally produced, you are neutralizing some of the acid and turning it into its conjugate base, and so you can end up with a buffer that way as well. So working out a pH in the buffer region is, first off, you have to sort of recognize that you're in the buffer region. So in this question, you can see you're given 30 milliliters of this 0.1 acetic acid, and it can be neutralized with 30 milliliters of the same concentration of base. So then it's asking you what is the pH when 10 milliliters of this base is added. And so you can see that 10 milliliters is well before the 30, so you're not neutralized. And you're somewhere in that region where it's partially neutralized, which means you have a buffer. So again, I like doing little ice tables to keep things straight. So I'm going to start off with my acetic acid here. And I'm going to add some sodium hydroxide and make the neutralization, which of course is quantitative. You're going to end up with CH3COO. You're going to have some sodium ions and of course the water from the neutralization. Now we're really only interested in these two because those are the parts of the buffer, right? That's the components of acid and conjugate base that make a buffer. So let's figure out how many moles of each we have here. So up here we have 0.030 liters, and we have 0.1 moles per liter. So that means that's 0.0030 moles of the acid. And then the same thing, we got 10 milliliters of 0.1, so that's 0.010 liters times 0.1 moles per liter, and again it's 0.001 moles of the sodium hydroxide. Great, so we can stick that in down here. We've got 0.003 moles of the acid. We got 0.001 moles of the base, and we got none of these to begin with. And then, of course, we're going to go minus x plus x. Good thing about neutralization, it's always going to be one proton at a time. And so what we'll have here is the sodium hydroxide, of course, going to get all used up. That means the x is 0.001 moles per liter, which means that this guy here is going to be 0.002 moles. And over here, we're going to have 0.001 moles of the conjugate base. And these we don't care about, so just ignore them. Now, to finish this off, to work out the pH, of course, we can use our relationship between the acid, which and its base, right? So the acid is the CH3COOH, right? And the conjugate base, CH3COO minus, and of course, the protons, right? So again, we want that part, so we'll rearrange things here. So we got Ka times the concentration of the weak acid all over the concentration of the conjugate base. So the Ka is 1.8 times 10 to the negative 5. The concentration of the acid is 0.002. Well, it's actually the moles, but remember the liters will cancel out, so it doesn't really matter. And then over here we've got 0.001 moles as well. And so what we'll have, I guess, is double. So 1.8 times 10 to the negative 5 times 2, which is 3.6 times 10 to the negative 5 moles per liter for H+. And then, of course, our pH is the negative log of that, which turns out to be 4.4. Yay, we did it. Alrighty, finally, just to finish things off, to go full circle right back to where we started with acids and bases. Once you pass the equivalence point, what you're going to end up with is excess of your strong base in this case, or strong acid, and determining the pH after the equivalence point just comes down to this strong base because it's going to vastly overwhelm any weak base that might be the result of the salt that's in the solution. So it's pretty simple once you recognize that. In this case, we have 30 milliliters of 0.1 acetic acid, and it can be neutralized with 30 milliliters of the 0.1 sodium hydroxide. So after 30 milliliters has been added, then it's just going to be sodium hydroxide really in there that's determining the pH. So the question is, what is the pH when 40 milliliters of base is added? And of course, that's 10 milliliters of extra base that is in there now. So what you do is you just dilute that excess base. So we have 10 milliliters of our 0.1 molar sodium hydroxide, and we're going to dilute that into the total volume now, which is 70 milliliters. The 30 plus the 40 makes 70, right? And so the concentration of that is 0.1 times 10 divided by 70 equals, so we have 0.014 moles per liter sodium hydroxide. Great. So since that's a strong base, then it's pretty simple to come up with the pH, right? We just take the negative log of that, because that concentration is still going to be the same as the hydroxide concentration because it's a strong base, right? So the POH there is the negative log, so that's the negative log of 0.014, which is 1.8, which means that our pH is going to be 14 minus that, which is, what's that, 12.2? 12.2. Yay, congratulations. You made it all the way through equilibrium with acids and bases right to the very end. We'll see you soon.